Hey guys, what's up? Welcome to the last tutorial for linear algebra. It went by so quickly, and today we're going to be doing probably the most important tutorial. We're going to be getting into the real meat and potatoes of linear algebra, in my opinion. Eigenvalues and eigenvectors. Really important, you know, like I say about everything, really important, but they're important, and they're cool, like, you know, we'll see. So, again, any problem with my email's there, give me an email. If you want an extra video during review week or something, study week, where I do some more questions that you might have trouble with, just email me and let me know. Email me a problem, say, look, solve this, man, and I'll just put in a video, like, I don't care. So, problem one is going to have us find the characteristic polynomial of a matrix A, and from that we're going to find what the eigenvalues of this matrix A are. Okay, so characteristic polynomial, you should know from the lecture that the formula looks like this. Maybe the notation a little bit different. Some people use a capital I instead of a script 1 or a blackboard 1, people might call it. And because we're in 3 dimensions, if we're being specific, we should just have a subscript 3 on the thing. But it's no big deal. So, I'm just going to go on a rant immediately. And we're going to see, just because I think people don't see it as clear as it really is, why this is so important. You know, how do we, where do we get eigenvalues and eigenvectors from? And how does it turn into this equation all the time? And so, blue writing, if I'm writing in blue from now on, it means it's not relevant. I'm just talking and hoping that it's helpful in some way. So, blue box here. I'm just going to explain where this equation comes from. Determinant A minus lambda times the identity in the characteristic polynomial. Well, remember, what we're trying to do is solve an eigenvalue problem, or the eigenvalue problem, however you want to say it, which is basically, I have a matrix or a linear map, and what I'm looking for are solutions to this equation for the matrix A, where this is just a vector. Right, the 2 v's here are the same vector, and lambda is just a scalar, i.e. just a number, a real number. Lambda is not a matrix, and A is a matrix. So what this equation is asking me here, if I were to solve it for a matrix A, is to find the vectors and the lambdas, right? So find the vectors and the numbers, such that when you apply A to the vector, it's the same thing, it's just multiplying that vector by a constant. Okay? Because, when you have a linear map, in general, you're not just multiplying by a constant. You're adding and subtracting things, whatever. So, finding these vectors and the scalars that make this equation work, it's an important problem. How do we solve an equation like this in general? And so, because it's a matrix equation, it's kind of complicated. I can't just bring the lambda over and factor out a v, because A and lambda aren't the same thing. A is a matrix and lambda is a scalar. So what I have to do is turn lambda into a matrix. And I do that by knowing that if I apply the identity to a vector, it's the same as doing nothing. So this is like multiplying by 1, right? By multiplying by the identity matrix. And now, if I just bunch the lambda and the identity matrix together, now I have a matrix on one side, a matrix on the other side. So I can bring this guy over and factor out the v vector, so that's equal to 0. Okay? So that should be so good so far. We've gone from writing out the actual problem to writing it like this by using a little trick. And now how do we solve it? Well, we should know that what this equation is saying is that this matrix here, this new matrix that we've made by subtracting this matrix from A, must have a kernel, right? Because this matrix times some vector v is equal to 0. So the matrix applied to a vector is equal to 0. So that means this vector must be in the kernel. Okay? The matrix maps it to 0 when it itself isn't a 0 vector. So if the kernel is not empty, right? There's at least something in there, specifically v. The kernel isn't empty, and so some of you might remember that if the kernel is not empty, the next step in this logic chain would be the kernel is not empty, A not invertible. A not invertible means the determinant of A has to be equal to 0. Sorry, I don't mean A here. I mean A minus lambda I. And the determinant of A minus lambda I. Exactly like this. So, what we get is that by knowing stuff about kernels and invertibility, I can actually now begin to solve simple equations that involve matrices. Solving matrix equations now. And this is precisely where the characteristic polynomial comes from. The determinant of A minus lambda I. Determinant of A minus lambda I. So, let's actually do it. I'll write out what lambda I is here. And in 3D, lambda I is just going to be lambda on the diagonal. 0 everywhere else. Just like that. And so that means A minus lambda I is going to be the matrix A beside me. 8 minus lambda here. Minus 1 minus lambda here. Minus 4 minus lambda here. 3 minus 3. Okay. Here's our matrix. We have to take the determinant of this. And so, we remember some stuff about determinants from tutorial 10, I think. And we know that we can find the determinant of this by taking the dot product of the first row with the cofactor vector along the first row. And I will just write it out. So I take my first entry of my first row, and I'm multiplying it by the cofactor expansion along the entry 1, 1. Then the second part of the first row times cofactor expansion along this entry, and minus 3. So last guy multiplied by the cofactor expansion along this guy. And if we remember our cofactor expansions, C j is equal to minus 1 to the I plus j determinant of aij, where we make aij by deleting the ith row and the jth column from A. Okay, so if you're not familiar with this stuff, obviously go back and watch that tutorial. But just writing out what happens here. Right, so I'm going to get 8 minus lambda, C11 now. First part's going to be minus 1 to the I plus j, so 1 plus 1 is 2. Square bracket, because I'm going to have some stuff inside. Now I need to take the determinant of C11, or sorry, A11, which means I look at A11 here, I delete the row and the column that's on. And now I take the determinant of the submatrix. Okay? So doing that means I have to take the determinant of this submatrix, which is going to be minus 1 minus lambda times minus 4 minus lambda minus 3 by 6. There we go. That's our first guy. Second guy here now, plus 3, square bracket. So now I want to delete this middle row and this top, sorry, this middle column and this top row. Take the determinant. So that ends up being minus 6 times minus 4 minus lambda minus 3 by 12. And the last guy. So minus 3 times cofactor expansion. I forgot here minus 1 to the I plus j. So b12 means 1 plus 2. And here I should also have a minus 1 to the 1 plus 3 here. Easy to forget. And now I need to get the determinant of the submatrix when I delete the first row and the third column. So make the determinant here. So minus 6 times 6. Minus 1 minus lambda times 12. And like, you know, in theory, you could keep going. And you could actually do this all out and multiply your lambda and find the characteristic polynomial. But to be honest, like, I mean, if you can multiply this out, there's no problem with you making this a little bit faster by using an online tool. This is a particularly manky calculation because the matrix A here has no zeros in it. So when we take the determinant, like, there's no zeros, so we've got to take everything, you know, there's no simplification by doing the cofactor along a certain row or column. There's no zeros anywhere to make it simpler. So that's why this is manky. The way you can simplify it is by row reducing A in a very particular way, and keeping track of what you do in your row reduction. But honestly, we're just going to plug it in. So let me pull that up. Okay. Here's a website. How I found this was by Googling characteristic polynomial calculator. Do you know, there's so many websites that are available here. I mean, this is just one. If you go to here, like, you see the calculators for everything. Rank of a matrix, eigenvalues, eigenvectors. Like, learn how to Google. So, to find the characteristic polynomial using this website here, you can specify the size of your matrix, 3 by 3, and then you just plug in what your matrix is. So that's easy. Minus 6, 1, 12, 6, minus 4. And I want to factorize the polynomial, if possible, and calculate. Here we go. So, this is the characteristic polynomial. Now they've used x as the variable instead of lambda, so we're going to be careful and not copy this down directly. My laptop started having a spasm. So I've written down the characteristic polynomial here. Let's just finish that off. Characteristic polynomial of A. Now, one thing I want to say very quickly. Don't confuse the c here of the characteristic polynomial with the c of the cofactor expansion. Completely different things. Completely different things. Okay, just in case anyone wants confused. So, found the characteristic polynomial. Now we need to show that these are the only eigenvalues of A. Well, to do that, we need to solve the characteristic equation. And what's the characteristic equation? The characteristic equation, when you take the characteristic polynomial and let it equal 0, and you solve for lambda. So, I want to solve minus 2 squared times lambda plus 1 equals 0. Well, either, I've got something times something equals 0. That can only happen if the first thing is 0, or the second thing is 0. If the first guy is 0, then I get lambda minus 1. And this is my first eigenvalue, my first solution. I'm going to call it lambda 1. Okay. Here's first eigenvalue. Then we've got the second case, which is that this guy is equal to 0. So if lambda minus 2 squared is equal to 0, we can forget about the squared. We get lambda is equal to 2. And so that means our second eigenvalue will be 2. Perfect. Part A done. So, part B, quick. State the algebraic multiplicities m lambda 1 and m lambda 2 of the eigenvalues lambda 1 and lambda 2 respectively. So the algebraic multiplicity is go to the characteristic equation, you look for the term associated with the eigenvalue you're talking about, and you count how many times it's a root of the polynomial. So for lambda 1, what I do is I go to my lambda 1, which is minus 1. This is the part of the characteristic equation, or characteristic polynomial that contains this eigenvalue. And you can see it's to the power of 1 here. So that means m lambda 1 is 1. M lambda 2, on the other hand, I go to the eigenvalue 2. This is the part of the characteristic polynomial with the 2 in it. And it's raised to the second power, which means that 2 is a double root of this polynomial. So the algebraic multiplicity of that 2. And I want to show, roughly speaking, what being a double root means. Really simple to use. Online, just log on, just go onto the website and click go. And you can just plot any equation you want, as long as it's a one-dimensional equation. You need GeoGebra for 2D and 3D equations. So, what does being a double root mean? And what's this algebraic multiplicity stuff? So if we plot what our characteristic polynomial is. Oops. I'm sorry if my fingers are just covering the webcam. The webcam here is built into the keyboard. So if I pop you down, it just looks like a normal keyboard, and one of the keys has a camera on it, and it pops up like headlamps in an old car. So what we have here is the equation, or the polynomial, and the characteristic equation is when it's equal to 0. So when it's precisely touching the horizontal axis here. And so you can see it passes through it when x is minus 1 and when x is 2. So my two eigenvalues. Now, I can make any polynomial go through any point I want by 2 seconds. Okay, so I can plot any polynomial I want and make it go through the points I choose by just writing it like this. So if I want my polynomial to go through the point -3, -2, and -1, I just have to write x plus 1 times x plus 2 times x plus 3. And in particular, if I take this equation now and I were to put an a here, just as a variable, I can add a slider which allows me to change what a is, and you can see I can change where the third root is. So instead of it being a 3 now, it's going to be a plus 0.5. If I increase this all the way up, I can make the root be, 6.4 or whatever. Now if I have a double root, or sorry, before double roots come, you should note that this isn't the only polynomial that goes through these points. I can add a minus sign here and not change anything. I can multiply by 10 here and not change anything about the roots. I can multiply by -100, and they still all have to go through -2, -1, and whatever I make a. Okay? So, double roots then would be, if I have a squared here, nothing changes about the roots at all, right? Nothing changes. But now the polynomial comes down through -2, and before it goes through -1, right, it goes up, it's about to hit -1 at the 0 axis, but it curves precisely on -1 like that. And that means, I just type the red line, that means that there's a double root here. Okay? There's actually 2 roots of this polynomial, and they're both precisely at -1. So if I delete the squared here, and I take my a, and I slowly make a 1, we can see exactly what happens. I have 3 roots. I'm coming in. Still 3 roots. And now as a becomes 1, the 2 roots disappear, and they merge at 1 into exactly 1 root. So 2 roots become 1. So there's actually still 2 roots. They're just both at x plus 1. Or sorry, they're both at x minus 1. So, purpose of that node was to just show you that that these algebraic multiplicities mean something. Okay, it means something for the squared to be here. It means that this eigenvalue is going to have 2 eigenvectors associated with it because it's a double root. Okay, it's not just 1 root; it's 2 roots at the same point. Okay, alright, see. Now we're going to go finding the eigenspaces for each eigenvalue. So remember, I have lambda 1 equals -1, lambda 2 equals 2. So what I want to find here is EA minus 1 and EA2, or epsilon A minus 1, epsilon A2. So they're going to be the kernel of our matrix that we found earlier. So that's easy. We just need to sub in the lambdas in the matrix we have up here. Right? So A minus lambda 1 times I just means sub in the first eigenvalue here for these lambdas. So if I do that, I'm going to start off with lambda 1 equals -1 first. And so what I need to do to find this guy, find the kernel, I want to find the kernel of ace minus -1. Then here I'm going to have a minus 1, minus 1, minus 1. And here a minus 3, minus 1. Rest of the entries are minus 6, 12, 6. Okay. So let's look at this matrix in more detail. 8 minus minus 1 is 8 plus 1. 9 minus 1 plus 1 is 0. Minus 3 minus minus 1. Whoops. Should be minus 4. So minus 4 minus minus 1 is minus 3. And so remember that the kernel of some matrix M is the set of all x such that mx equals 0. Okay? So the kernel of this matrix is going to be the set of all vectors such that when we apply the matrix to it, we get 0. So we might as well write that in augmented matrix form, like this. And so if we row reduce this, we'll be able to find equations for the vectors x that satisfy the augmented matrix. So vectors that when I multiply them by this matrix, it's 0. So let's row reduce. First thing I'm going to do is divide everything by 3. Everything to multiple of 3. That'll be enough. And nothing happened to the 0 because 0 times 3 is still 0. Let's see. It'll be better on my room here. So, what's the first thing I want to do? Well, I can see that I can eliminate the 4 here by using the second row, and I can make this 3 into a 1 and maybe simplify things by adding the second row to it. So I'm going to take row 1 and replace it with row 1 minus row 2. I'm going to take row 3 and I'm going to replace it by row 3 plus 2 times row 2. Okay? So 3 plus minus 2 is 1. 1 plus 0 is 0. Sorry. Adding here. 3 plus minus 2 is 1. 1 plus 0 is 0. Minus 3 plus 1 is going to be minus 2. Then I'm going to leave this guy alone. And now I want to add minus 4 to 4, which gives me 0. Add 0 to 2, which is 2. And now I add 2 to minus 1, which gives me 1. Nothing happened to the 0. Wonky. So, next step. What I can do is not follow what I have written out and make it harder for myself. Okay. I did this wrong, so good thing I have my notes beside me. Wrong. Yeah. I mean, like that I divided by 3 here. That's just a lie. That should be minus 1. So now if I'm adding the second row to the first row, I'm going to get 1 here, and 1 plus 0 here, which is 1. And minus 1 plus 1 is 0. Cool. Alright, that makes me happier. So now I can just add the third row to the second row, and you'll see what happens. So I get 1, 1, 0, minus 2, right, what I do here. So I'm taking the second row and replacing it by the second row minus the third row. So minus 2 minus 0 is minus 2. Then 0 minus 2 is minus 2. And then 1 minus 1 is 0. Cool. So now I see that the second row is linearly dependent on the first row. So if I add 2 times the first row to the second row, it gives me a row of 0. So they're linearly dependent. And so what I'm going to do is just bring the third row up to the second row and put the row of 0 on the second row. So what's happening is row 2 is being replaced by row 3, and row 3 is being replaced by row 2 plus 2 times row 1. And so that makes our matrix look like 1, 1, 0, 0, 2, 1, 0, 0, 0. And now our equations are simple. What are our equations? Well, I just need to take these rows and let them be equal to the 0 on the right hand side. So I get 1 times x1 plus 1 times x2 plus 0 times x3 is equal to 0. And on the second row I get 2 times x2 plus x3. 0. Now, here we have 2 equations. We have 3 unknowns. Therefore, 1 degree of freedom. Okay. All this will be writing in shorthand because you don't need to write it. So let x1 be equal to t. And my degree of freedom, t, any real number. So our first equation becomes t plus x2 equals 0, and that implies x2 is equal to minus t. Third equation becomes minus 2t plus x3 plus x3 equals 0, and that implies that x3 is equal to 2t. And that means that the kernel of A minus lambda 1 and I is going to be the set of all vectors that look like t minus t and 2t such that t is a real number. Okay, I've found my kernel. And so I can obviously factor out t to get 1 minus 1, 2. And so this tells me that the kernel is going to be the span of just this vector right here. And so that tells me that the eigenbasis is going to be just the span of this vector. So I have that b lambda 1. Yeah, sorry. X A lambda 1, which lambda 1 is minus 1 here, is going to be just this vector alone. So that's the basis. The basis is just this vector. And so, sorry, this is the eigenspace. I don't know why I'm so bad today. I just have a t here still. This is the eigenspace. It's the span of this vector here. That's the t more. Okay, and the eigenbasis now, which we write with a b, it's going to be the space, the eigenbase, generated by this one vector. Basis of lambda 1 is going to just be this vector. Okay, perfect. And I've run out of space. Let me make some more. I'll make more space to the right. And hopefully now I won't mess anything up. So next thing we have to do is get the second eigenspace and the second eigenbasis. We want to look at the kernel of a minus lambda 2 times I, or the identity, and lambda 2 is equal to 2. So what we want to do, find EA minus 2 be the kernel of let's see here, forgetting it every time. So ace minus 2, 3, minus 3, minus 6, minus 1, minus 2. So 6, minus 4, minus 2. Okay, so again, we're going to use the augmented matrix approach. Get this fastest. So we're going to have a 6 up here. This guy will be a minus 3. And our last one will be a minus 6. And we're solving this for vectors that get mapped to 0. And I shouldn't have an equal sign here necessarily, because I'm solving to find the kernel. This isn't just equal to the kernel. So first thing I'm going to do is divide by 3. So get a g 1 minus 1. Get this thing. And what should we do here? Well, I can add the second row to the first row, or the first row to the second row. And I know the row 2 becomes row 2 minus row 1. And I also think I'm just going to add 2 times the second row to the last row to get this 4 to be 0. So row 3 is going to be row 3 plus 2 times row 2. 2, 1, minus 1. Now I have, this should be a plus. Minus 2 plus 2 gives me the 0 here. Minus 1 plus 1 gives me the 0 here. And 1 plus minus 1 gives me another 0 here. Row 0 for free. And now row 3 is going to be 4 plus minus 2 and 2 is 0. 4 plus minus 4. 2 plus minus 2 is 0. Minus 2 plus 2 is 0 again. So immediately we're done row reducing. We've got 2 rows of zeros. Very cool. And the equation we have here is that 2 times x1 plus x2 minus x3 equal to 0. And so one equation, one degree of, well, one equation, 3 unknown, 2 degrees of freedom. Okay, so let's say x3 equals t and x2 equals f. And so that means 2x1 plus t That means 2 times x1 is going to be f minus t. So x1 is going to be f minus t all divided by 2. So we immediately know what our kernel is. It's going to be set of all vectors that look like f minus t over 2. We want to here ft is a real number as always, and I can pull these apart into their respective parts. So f times the first vector is going to be a half f over 2, and then 1 here and 0 here. Then I'm going to have t times minus a half here, minus 2 over 2, 0 here. That's ft, the real number. And this is my eigenbasis, or the eigenspace. This is the eigenspace. Epsilon A2 is going to be literally this. Right, you just write it again. Or I should have done before, you can write it as a span of 2 vectors. Span of my first vector. My second vector. Getting it right this time. The eigenbasis for lambda 2 is going to be these 2 vectors. Okay, so that's the question done. Day that the eigenvalue that had a multiplicity of 1 under 1 has only one basis vector, while the eigenvalue with an algebraic multiplicity of 2 got 2 eigenvectors, or 2 vectors in its eigenbasis. So that leads right to the next question. Which is to find the geometric multiplicity of these. So in general, d lambda is the dimension of the eigenspace of lambda. So d lambda 1 is going to be the dimension of EA lambda 1. And we have right here, it's the span of just 1 vector, the base of generating it at 1 vector, so the dimension is 1. D lambda 2 then is the dimension of A lambda 2. And we'll just go over and look at this. Span of 2 vectors, the base of generating it had 2 vectors, so the dimension has to be 2. Job done. And now part E is going to have us talk about the algebraic multiplicity, the geometric multiplicity, and that has something to do with A being diagonalizable. So if you know this stuff with lecture notes, then It's going to be a reminder or a recap. So if we think about the algebraic multiplicity we had here, writing them all out now. So on the top of our algebraic multiplicity, not bottom, our geometric multiplicity. We can quickly see that if I add the algebraic multiplicity together, that's 1 plus 2, and it's 3. And 3 is the dimension of the space we're working in, or 3. Okay? 3 is also the size of our matrix A. So, I don't know why I wrote n by n. A is a 3 by 3 matrix. So, in general, you might guess that if I add all the multiplicities of all my eigenvalues, the algebraic ones, that it will just equal the size of the matrix. So if A was an n by n matrix, then adding all the multiplicities together should give me n. And that's actually always true. So for the algebraic multiplicities, if you add them all together, you'll get n always. Doesn't matter what your matrix is, doesn't matter what your linear map is, it's always true. And we can see that in this case, that if I add the geometric multiplicity, I also get 3. And that the algebraic multiplicity and geometric multiplicity are equal. But this isn't always true. Okay? So just remember that this isn't always true. In particular, the geometric multiplicities might be less than the algebraic ones. In this case, it's not true, but it can happen. And if it happens to be true, this fact implies a diagonalizable. And if it's not true, then A isn't diagonalizable. So this is the argument. Okay? I would recommend writing it in words, not how I've written it here. Very loose, very bad notation. But you just need to explain, right? The geometric multiplicities are the same as the algebraic multiplicities. Therefore, the matrix is diagonalizable. And if it's not true, you just say they're not equal, so it can't be diagonalizable. You might wonder why at this point, if you don't already know. You're about to see this in the next part, part F. So, part F is going to be to determine the invertible matrix P and the diagonal matrix D, such that A is equal to P, D, P inverse. D is a diagonal matrix. So, this being true, the fact that I'm able to find a P and a D to write this down means that A is diagonalizable. I can come up with a matrix so that I can turn A into a diagonal matrix D as long as I have P and P inverse on the other side to this. So this condition here is being diagonalizable. Okay? A being diagonalizable means you can do that. You can find the P and the D to do that. And they're not unique. Okay? So you can find many P and many D to make your matrix A look like this. Yeah, you can. So in this question we can make exactly 3. So you'll see why. So it turns out, I want to be careful here. If we consider what we found here, we found lambda 1 is 1, lambda 2 is 2, and we found 3 eigenvectors. So the first eigenvector belonged to the first eigenvalue, and it happened to be this guy here, 1 minus 1, 2. And v2 and v3 then, our two other eigenvectors, came from the second eigenvalue, which had a multiplicity of 2, we found. So those are a half 1, 0, minus a half 0, 1. I've got a half 1, 0. And here are my 2 eigenvalues and my 3 eigenvectors. Now we want to find a basis. Okay? First time I've said this, but this looks like the change of basis formula. So I want to find a basis with a change of basis matrix P, such that in that basis A looks like a diagonal matrix. And it turns out that the basis to do this in is the basis made from the eigenvectors here. So if I define my basis B to be the basis generated by 1, 1, 1, 2, 1 half, 1, 0, and minus 0, 1. If I look at this basis here, you can find something interesting. If I take A and multiply it by v1, my first basic vector, well, I just solved the eigenvalue equation. So I know that if I apply A to v1, that should look like just multiplying v1 by minus 1. So that's going to be lambda 1. If I apply A to v2, that can be the same as doing lambda 2 times v2. If I do A times v3, that can be lambda 2 times v3. Lambda 2 is a double eigenvalue. So compare what I just wrote there to the thing we started off with, the eigenvalue problem, AV equals lambda v. So that's how I know those 3 equations. And because of this fact here, we get that if we defined these to be our basis vectors, right, precisely how we do right here, then A in the basis B should look like lambda 1, lambda 2, and lambda 3. 0 everywhere else. Act like this. Okay? Hopefully this makes sense. Because if these are the basis vectors, v1, v2, and v3, A is defined by what it does to those basis vectors. And all it does to those basis vectors is multiply them each by an eigenvalue. And of course, I mean, lambda 3 doesn't exist. So why do I write it down like? I'm actually having an issue here with my laptop, to be honest. The eraser's not working. Stuttering. But we'll make it through to the rest of the tutorial. So, this is what A should look like in the basis B. It looks diagonal. So, my idea, not my idea, I mean, I know that this works. So my idea to use this basis here was correct, okay? This is the basis that's going to give us the diagonal matrix D. So this is our diagonal matrix D. Right? A in the basis B. And I can get to it by using a change of basis matrix P, where P is just built out of the eigenvectors of the basis. So P is just going to be 1, 1 minus 2, a half, 1, 0, and minus a half, 0. That means A is going to be P, D, P inverse, where D is diagonal. And this is important, right? Really important. So what we've done here in this question, I mean, I know it's long and arduous, but what we've done is we found the eigenvalues and the eigenvectors of our matrix. That in itself is really important because they mean things. I know it's not clear what they mean at the moment, but they do have a lot of significance. One of the things that they do is that if I build a basis with the eigenvectors of my matrix, that's the perfect basis to make that matrix look diagonal. So I start off with my matrix A, which is not diagonal at all, right? I'm going to write this out explicitly. Another one with minus 1 and B for 2. Like that. I've taken my matrix A, which had no zeros in it, and I found a basis with its eigenvectors that now makes matrix A look just stupidly easy. I mean, remember we had to take the determinant of A minus lambda I earlier and it was horrible? If I had to take the determinant of this, the determinant of this is just I multiply all the diagonal entries together. So that's be minus 4. So way easier. So that's why this is important. And so like, if you want to, right, you can check this. You can find P inverse, and you can take these three matrices and you can multiply them together, and you can definitely check yourself that if you multiply it all out, you'll get back A. You'll get back that horrible matrix there. And so what you should know now is how to find the eigenvalues and the eigenvectors of a matrix. It's really the culmination of every introductory course to linear algebra. Because now you're at a point where you can start using things about eigenvalues and eigenvectors to talk about complex matrices and matrix equations and solving really advanced problems in maths that look really hard when you write them down without matrices, but all of a sudden look really easy when you write them down with matrices, and you just think about the eigenvalues and the eigenvectors. So the last thing I'm going to talk about before the tutorial ends, you never have to hear my voice again. Okay, I'm just going to talk about where the term eigenvalue and eigenvector came from, and obviously then eigenbasis, eigenspace, eigen whatever. It's actually a German word, so eigen is a German word. Means something like proper or characteristic or own. And it was, the first person to use the word eigen to talk about them is a guy called David Hilbert. So before then, people used to call them proper values and proper vectors. And David Hilbert just called them eigenvalues and eigenvectors, and everyone just sort of went, yeah, that's it now. And I mean, fair enough. So here's a Wikipedia page of the things named after this guy Hilbert. Crazy mathematician. You need way too much stuff. Kind of ridiculous, right? And all of this is just beyond mathematicians today. He's an absolute giant in the math world. But he's got some interesting stuff, just some cool things I thought I'd introduce you to. So, he has a paradox where he considers a hotel that has infinite rooms and possibly infinite guests, depends on which of the paradoxes you're talking about. And it's just crazy, okay? Hilbert was one of the people who thought a lot about what infinity meant. I mean, we haven't touched anything about that in linear algebra, but it's all related, I promise. Another thing associated with Hilbert would be this pretty thing here. You see, this is a Hilbert curve, or space filling curve. And what's going on here, looks kind of simple, but it's actually crazy. And if you're interested in learning about those two things, the infinite hotel paradox or space filling curve, you just type number file Hilbert on YouTube, the first two videos, got you covered. I really would recommend you just watch math videos, because math isn't just linear algebra lecture. It can be fun sometimes. So, I mean, whenever you learn something in a module in math, you should just be YouTubing it. You will find some really good stuff. And if you're really that way inclined, if you really actually enjoyed linear algebra, I mean, you have to watch this series now. And you'll just be able to visualize everything that we've done, right? Or everything you've done in linear algebra. That would have just been equations. You can now just see. It's great. So give it a watch. You will learn, and you'll recap a lot of stuff. And other than that, best of luck in the final exam.